Welcome to the lectures for Class 11. This is the first part of two classes on search based on the Chapter 3 of our Russell and Norgate text. For this lecture, we're going to look at problem-solving agents more formally and look at problem types, describe how to formulate problems more formally, and look at some example problems. And then we'll start looking at some of the basic search algorithms. Today we'll start with breadth-first search, and for the next class we'll pick up with the other kinds of basic search algorithms. So let's start by defining a problem-solving agent more formally. Now, this is the kind of agent where we present the problem, it figures out what to do in terms of like an action sequence, and then executes it. This is called offline problem solving. In other words, we know the entire problem ahead of time. So this would be contrasted with online problem solving, where we don't have complete knowledge and we have to do something, take another look, do something more, and so forth. So for our offline problem solving agent, the idea is that we have an action sequence which is initially empty, a state, a goal, and a problem. Now, what we want to do is every time we get a percept, we update the state and then set up our sequence of actions. So if the sequence is empty, then we're going to start by figuring out from our current goal, current state, what our goal is. We'll figure out the problem to solve from the state and the goal, and then we'll search the problem's formalism and come up with a sequence of actions. And the recommended first act, of course, would be the first action in that sequence given the current state. So basically return the action, iterate, do it again. So for example, let's imagine that we're on a holiday in the southern European country of Romania, and we currently find ourselves in the city of Arad, but our flight leaves tomorrow from Bucharest. So our goal is to be in Bucharest so we can catch the plane, and we'll formulate the problem so that the states are the various cities. In other words, we're in Arad or we're in Sibiu or something like that. And the actions, that is, the things that can take us from state to state, would be to drive between cities. And our purpose, therefore, is to find a solution which would be a sequence of cities, really a sequence of actions that would take us from Arad all the way to Bucharest. So, for example, if we have this map of Romania and roads with distances, one route might be to start in Arad here, which has the circle here to start, go to Sibiu, Făgăraș, and then to Bucharest. So that's one possible route, and the action sequence would be drive from Arad to Sibiu, drive from Sibiu to Făgăraș, and drive from Făgăraș to Bucharest. Well, that's just one particular problem, but of course there are lots of different problems, and we can describe these problem types a little more systematically. So if our problem is deterministic, that is not stochastic, and is fully observable, then we'll call it a single state problem. In other words, the agent knows exactly which state it will be in, and the solution is a sequence of actions that gets us from our initial state to a solution to a goal state. A non-observable problem is one which is called conformant. That is, the agent may not know where it is, and if there is a solution, it's going to be a sequence. So a conformant problem basically means we have to be able to start anywhere, and our solution has to work for wherever, if it's possible to have a solution, our solution has to work wherever we start. That's what we mean by conformant. Now, if we have a non-deterministic and or partially observable problem, then that's called a contingency problem. It's contingent in the sense that we take some action and then we get new information, a new percept about the current state. So at any particular point, our solution is a contingent plan or a policy. It's a contingent plan in the sense that we've got the solution planned out, but based on what happens, what we learn in a new state, we can change our plan. And here we can often interleave search and execution. That is, we search, then execute, get some new information, redo the search, execute again, and so forth. And finally, we've got an unknown state space, which we can call an exploration problem. And we've already called that online. In other words, we don't know what the states are to start with. And every time we take an action, we find ourselves in a new state, and we have to replan. Well, let's start with a fairly simple world, the vacuum world that we're already familiar with. And at least in our first simple case, we know that there are only two locations, left and right, and the vacuum can be either in left or right, and the space can either be dirty or clean, which means there are a total of 8 possible states. So for instance, the first state is the vacuum is in the left side and both left and right are dirty. State 2 is both are dirty and the vacuum is on the right, and so forth. So that's the state space. And let's think about if our problem was a single state problem. In other words, deterministic and fully observable, we know where we are. So let's say we start in number 5, state number 5, where the vacuum cleaner is on the left, it's clean there, and the dirt is on the right. So what's the solution? Well, pretty clearly, right? You move right and then suck up the dirt. Now, so that one's relatively easy. What if, on the other hand, we had conformant? So in this case, we could start in any of 1, 2, 3, 4, and so forth. We don't know where we're going to start. And so if we start in any of these, if we do the action right, we'll end up in 2, 4, 6, or 8, but we don't know which one. Well, why is that true? Because we start in 1, 3, 5, or 7, we'll end up in one of the even-numbered states, and if we start in an even-numbered state, then we'll stay in that state. So what we're looking for is a general solution, which would be a sequence of actions that would work to have both sides clean no matter which state we start in. And that's possible too. So no matter where we are, we move right, suck up the dirt, move left, and suck up the dirt. Now, if we're in an even-numbered state and we're already in the right, then the first action doesn't matter, and we'll end up we'll stay where we are and suck up the dirt. Then we'll move left and suck up the dirt, whether it's clean or not. If we start out in one of the odd-numbered states, we'll move right before sucking up the dirt, but at least we know that we'll make it back. What about a contingency? So let's say we started number 5, but basically it's possible that if we have a clean carpet and we apply the suck operator, then we can make it even more dirty. So what we want is to have local sensing of dirt in this particular location only. So can we come up with a solution, an action sequence there? Well, then we just say, just like number 5, we say right, but only if dirt, then suck. We don't apply the suck operator unless the floor is dirty, because otherwise we run the risk of dirtying the carpet. For the balance of this lecture, we're going to be focusing on single state problems. That is, we know where we're starting and we know what all the states are going to be. There isn't any contingency or anything like that. So if we have a single state, we can formulate the problem in terms of 4 items that define it. So the first item is an initial state. So for our get from to Bucharest example, our initial state might be at Arad. There's a successor function, s of x, which gives us a set of action state pairs. In other words, it helps us, it shows how you get from state to state via an action. So if our state is Arad, then we have an action Arad to Zerind, and we end up in Zerind, and so forth. There's a goal test, and that could be explicit. So for instance, our state might be at Bucharest, or it's implicit, there's no dirt. Remember, in the Wumpus world, our goal test was something like have gold and we're in location 1, 1. And the fourth item that defines a single state problem is the additive path cost. That is, as we're traversing from state to state, we need to add up the cost of executing that particular plan. Now, in the Romanian holiday example, that's pretty easy because we can just sum the distances between the cities. We could have other kinds of costs too, like the number of actions executed and so forth. And in the Wumpus world example, for instance, moving from one location to another cost us 1, and shooting the arrow cost us 10, and so forth. And so there's a, you can have a cost function, and we assume that the costs are going from step to step is going to be greater than or equal to 0. We can't take costs back. So a solution is a sequence of actions that leads from the initial state to a goal state. One of the main problems in artificial intelligence is representation. And here our representation problem is how to define the state space. Now, the real world is really, really complex. If we imagine the country of Romania and the roads, it's not so neat. The cities have streets with intersections, and maybe it costs a lot of time to get on the road to one city as opposed to another. Maybe there's construction going on one of the roads, or there's a snowstorm on one road and it's blocked, and so forth. So the real world is just full of detail that is going to be too complex for us to solve with these kinds of techniques. In fact, on almost any artificial intelligence technique. So we have to abstract away from the real world into a state space that's suitable for solving problems. So this abstract state has to be equivalent to our set of real states, but simpler. And our abstract action is going to be a complex combination of real actions or equivalent to it. So if we, in our abstracted problem, think we have an action of going from Arad to Zerind, that represents a complex set of possible routes, detours, rest stops, snow, hail, big trucks on the road, and so forth. So for us to guarantee that we can actually get the solution, any real state of being in a rod must get to some real state of being in Zurind. In other words, it has to be possible to do that. And then our abstract solution, of course, is going to be a set of real paths that are solution in the real world. Now, it's true, of course, that each abstract action should be easier than the original problem. Otherwise, we're not going to be able to make the solution any easier for ourselves. But conversely, it's also true that solving the problem in the abstract may not necessarily solve it in the real world if there's some aspect of the real world that we're not really capturing. So rather than worry about the condition of roads in Romania, let's think about the vacuum world and its state space. So pretty simple world, and here we can start with a state, for instance, where the vacuum cleaner is in left and both sides are dirty, and we can see what happens. If we run the left operator, we'll back where we are. If we run the right operator, we'll put us in a situation where both left and right are dirty, but the vacuum cleaner is still on the right, and so forth. If we're here in this state, both left and right dirty and the vacuum cleaner on the right, and you run the suck operator, then we'll end up in a state where there's no dirt on the right, but there is still dirt on the left, and so forth. So remember that we had a total of 2, 4, 6, 8 states in our previous formulation, and all we're doing basically here is showing those same states, but with arrows that show the transitions between the states. And this, as an entirety, is called the state space graph. So let's go through and see if we can characterize this particular state space. So the states, well, they have integer, dirt, and robot locations. In other words, it's either dirty or it's not, 1 or 0, and the location is either left or right. So that could be 1 for left and 0 for right, and so forth. So we're going to abstract away from the fact that there might be a lot of dirt or a little dirt. How about actions? Well, our actions are going to be left, right, suck, and no op. Just stay where you are. What's our goal? Well, our goal is no dirt in either the left or the right. And the path cost, well, we'll just arbitrarily say that the path cost is 1 unit of cost per action and 0 for a no-op. Let's look at another more classic state space now, and that's the example of the 8 puzzle. And you may have actually played one of these puzzles. It's a square with 8 sliding tabs, and they can slide around. And the idea is it was sort of like an early version of a flat version of Rubik's Cube, if you like. And they start out in some random order, and the idea is to get them into numerical order. So here, what are the states? Well, they're the integer locations of the tiles. That is, we know that, for instance, in our start state, 7 is in space starting from the top 1, 1, and 2 is in 1, 2, and so forth. And we're going to ignore intermediate positions because all we're interested in is where the tile ends up after each sliding move. In terms of actions, we can basically we can think of where to move the blank. So if we move the blank where in the initial state up, then 2 will now be in the middle, and so forth. So we can think of it as moving the blank left, right, up, or down. and we'll ignore things like unjamming. These puzzles were fairly prone to mechanical error, and you kind of had to jiggle them to get the things to run again. And that's an example of abstraction, because we're just going to ignore that possibility. Our goal test is, well, are we in the goal state where the tiles are in numerical order? And that's a given. And the path cost is we can define as 1 cost unit per move. So it turns out that the optimal solution for some n puzzle, not just 8, is NP hard. So just solving this by brute force could take a long time. Here's another example, less prone to or susceptible to being characterized in terms of integer or propositional values, and that would be robotic assembly. So the idea is we have a robotic arm, and it can move on various axes. The arm can go backwards and forwards, the hand can rotate, and so forth. So what kinds of states would we have here? Well, we're going to have, instead of integer valued states, real valued coordinates of the robot joint angles and the parts of the objects to be assembled. The actions, well, those are continuous motions of robot joints, so we're going to have to talk about time and speed, things like that. The goal test, well, it'll have to be the complete assembly, and with the robot not being part of the assembly, obviously. The assembly has to stand on its own, and the path cost, we can say, is the time to execute. So that gives you some idea of the ways in which we can define single-state problems, and for the most part, we're going to be looking at problems that have discrete values for the states and actions. For this third and final part of today's lecture, we're going to be looking at tree search algorithms, and this really is sort of the classic heart of artificial intelligence. The basic idea is that we're going to have a single state problem. We're going to solve it offline through a simulated exploration of state space. In other words, we know how the 8 puzzle works, and we can figure out a solution. Given a initial state, known initial state, we can figure out a solution without having to actually manipulate the tiles. And then once we have a solution, we can execute the solution with the tiles. So how do we explore it? Well, we have our initial state. We'll look at the possible states we can get to from that initial state, and every time we get to a state, we will then expand to find out what states we can get to from there. For instance, if we were doing the Romanian travel, if we're starting in Arad, that's our initial state. The successor states would be the cities you can drive to from Arad. The successor states of those would be the cities you could drive to from those cities, and so forth. So it basically will keep expanding the states and examining the states to until we know that we've gotten to a solution node, the goal node. So more formally, tree search takes a problem and a strategy and returns either a solution, which is going to be a sequence of actions, or a failure. So we initialize the search tree starting with the initial state of the problem, which we've defined formally in the previous part of the lecture. And then iteratively we do the following. If we haven't reached the goal state and there are no candidates for expansion, then we failed because we have no possible solution. Otherwise, choose some leaf node for expansion according to our strategy, and we'll talk about those strategies in a moment. The classic ones are breadth first and depth first. We expand the new nodes from the leaf node, and we look at those. And if the node contains a goal state, then we can return the corresponding solution because we've got the sequence of actions that takes us there. Else, we expand that node and add the resulting nodes to the search tree. And then we loop back and keep looking at leaf nodes and expanding them until we find a goal. Or we fail because we can't expand leaf nodes anymore. So, for example, looking at our Romanian travel, we start in Arad, and we know we're not in the goal state yet, and we're able to expand the list of nodes. We only have one leaf node at the moment, that's Arad, and we can expand from that. So we've examined Arad, and we expand the leaves of Arad, which are the cities of Sibiu, Timisoara, and Zerend. And then we would recursively then expand from, Sibiu is a leaf node, we can expand it. It's not yet a goal, but we can see, we can create a new leaf nodes to add to our collection of leaf nodes to look at, which the cities that you can get to from Sibiu, and of course note that Arad is one of those cities, so we have a possibility of looping there. Okay, so that's the idea in the abstract. So how are we going to do it for real? I want to make the point that when we're implementing, states are the abstraction, and nodes are what we're going to implement to represent that abstraction. So a state is a representation of some kind of thing in the real world, like we're at Arad, or there's a particular sequence of tiles in the 8 puzzle. In contrast, a node is a data structure that constitutes part of a search tree that's going to correspond to a state in the problem. So a node is going to have a parent, unless it's the root node, our initial state. It'll have children, that is the nodes that it can expand to, unless it's you can't expand from it. It has a depth, that is how far down it is in the tree, and it's got some sort of path cost, because maybe the cost of going from node to node isn't uniform. We know that to be the case, for instance, in the Romanian holiday example, where the cost of going from city to city is not uniform, but rather is a function of the distance between the cities. So in terms of the 8 puzzle, here's a state of the 8 puzzle, a particular arrangement, and it corresponds as a corresponding node in our implementation that might, say, have a depth of 6. It has a cost of 6 because for the 8 puzzle, the cost of each action is a unit cost. It has a parent node and an action that gets us from the parent to this node, and so forth. So if you're in a particular node and we apply an expand function that creates new nodes, fills in these various fields, and using the successor function of the problem to create the corresponding states. In other words, each new node we create represents some successor state. So in general, and not really worrying about the strategy for the moment, what we'll do is define our general tree search as a function tree search. It's got a problem, which is basically the state space. It's got the fringe, which is our set of open nodes, the ones that we've created but haven't explored yet. and it's going to return a solution, which is going to be a sequence of actions or failure. So we create the fringe by basically creating nodes for the initial state of the problem and assuming the initial fringe is empty. And then, so if the fringe is empty, in other words, we examined all the possible nodes, then there's no possibility of a solution and return failure. Otherwise, we take the first node in the fringe, call that node. We will test to see if that node is a solution, and if that is a solution, then we'll return the node. Otherwise, we expand all the possible nodes that could be generated as successor states from this node and add them to the fringe. So how do we expand from one node to get new fringe nodes? Well, that's this one. That's this function. So we've got a particular node we're in, and we have the problem, which is basically the state space. And this is going to return a set of nodes which we're going to add to the fringe. So we start out by initializing successors as the empty set. And for each action and result in the state space, that is, from this node we can take some action to go to a successor state, we create a new node, we set the parent to be the current node, we set the action to be the action that gets us there, and we have this new state that's the result. We can calculate the path cost, which is either unit cost or the actual cost, and we increment the depth by 1 because we've now moved one level down in the tree, and we add S to the successors. And we do this until we've expanded all the possible states from the current state node. So that's how you do it. You generate the fringe and then add it to the for this particular node, add it to all the unexpanded nodes, examine the next node if it's the goal, and we're done. Otherwise, we expand it, and so forth. Now, I haven't really talked yet about how to choose which node to look at next, and that's called a search strategy. So the strategy is defined by picking the order of node expansion. We've got all these nodes on the fringe, and the question is which one are we going to look at next and expand. So what makes a good strategy? Well, we can evaluate it in terms of completeness, time complexity, space complexity, and optimality. So by completeness we mean, does it always find a solution if one exists? Right? And that's, you can think of that as analogous to completeness when we were talking about logic, predicate logic, and propositional logic. Time complexity means the number of nodes generated and expanded. Space complexity is the maximum number of nodes in memory at any one particular time. It might be that we can throw away nodes or not have to keep them, and or regenerate them. That'll cost time complexity, but it'll cut down on space complexity. And optimality means, does it always find a least cost solution? That is, there might be more than one solution, just like there are multiple ways to go to Bucharest, but we want to find the way to Bucharest that has the shortest distance. So time and space complexity are measured in terms of B, which is the maximum branching factor of the search tree. That is, if you imagine any particular state, you count the number of arrows coming out that take you to new states. How many possible actions are there that take you to new states? That's B, the maximum branching factor. D is the depth of the least cost solution. In other words, if we had the search tree expanded out and we identified all the solutions, D would be the depth of the least cost solution. And M is the maximum depth of the state space, which may be infinite. So for instance, in the 8 puzzle, you could keep pretty much going forever because you could keep cycling between 2 states. Or in the Romanian holiday example, again, we could keep cycling between 2 cities, and the tree eventually would have an infinite state space, until we run out of gas, perhaps. So we're going to focus here on what the book calls uninformed search strategies. That is, they use only the information available in the problem definition itself. There's no other kind of outside reasoning like we did with our Wumpus world. And the kinds of search we're going to be looking at today and in the next lecture are breadth first search, uniform cost search, depth first search, depth limited search, and iterative deepening search. And today and in this lecture, we're just going to look at breadth first search, and for the next class, we'll look at the other kinds of search. So let's talk about breadth first search. So here the strategy is to expand the shallowest unexpanded node. So basically the fringe is a first in, first out queue. That is, we're going to look at the oldest node in our queue first, and new successors go to the end of the queue. Let's see how that works. So if I have a state space that consists of the tree you see here with the states A through G, and we're starting in A, then what we're going to do is expand first. Well, A is the only node in our fringe, so we'll expand it, and its successors are B and C. Now, because we're going to do this, expand the shallowest unexpanded node, then we'll pick B, because that was the first one we expanded in front of C. We'll expand it first. We'll take a look at it and get D and E. Then we'll expand C and get F and G. Now we've looked at every node at the B and C level, that is depth 2, and we will, well, depending on how you count, this could be depth 1, depth 2, depth 3, and so forth. And now, since we've looked at everything at what I'm calling depth 2, we can look at the first node of depth depth 3, sorry, which would be D, and so forth. We look at D, E, F, and G, and that's it. So notice that that breadth first search works like a queue, just like we implement it. Every time we expand a node, we put the successor nodes at the end of the queue, and we're going to expand, choose a new node to examine to see if it's a goal or expand. We pick the oldest node in the queue. So what do we know about the usefulness or appropriateness of breadth first search? So first of all, is it complete? Well, yes it is, if the branching factor is finite. If the branching factor isn't finite, then you keep expanding infinite number of nodes at any particular level, which isn't going to work. But for pretty much most of the problems we're going to be seeing or could contemplate, the branching factor is finite, so therefore it's complete. It's going to find the solution, if one exists. How about time? Well, if we think about time, the first level will take 1 because there's one node for the root. The next level will have to create however many nodes there are equivalent to the branching factor, which is B. The next level will have b squared, because each one of these b will have another b. The next level will have b cubed and so forth through b to the d and b to the d minus 1, b times b to the d minus 1 when we find the solution, which we can say is on the order of b to the d plus 1. In other words, the time, which is equivalent to the number of nodes we have to create, is exponential as a factor of d. That is, the depth of the tree where we find the solution. How about space? Well, again, it's the same thing. It's order of the branching factor to the d plus 1, because we have to keep every node in memory. Now, in terms of optimality, well, by golly, yes, it is optimal if each cost is 1 unit per step. But it's not optimal in general. Why is that? Because, for instance, if there were a path from Arad to Bucharest that was short in terms of the number of actions taken, but really long in terms of mileage, it would reach that solution state before it reached a solution state at a deeper level of the tree that is required more transitions from city to city, but which might have a total shorter mileage. The other thing about breadth first search is that space is the really big problem. These kinds of searches can easily generate nodes at about 100 megabytes per second. So if you ran your problem for 24 hours, your little problem would generate 8,640 gigabytes of state space, which is probably not going to be tractable. So that's breadth first search, and in the lectures for the next class, we'll take a look at depth first search